In this video, I'm going to do a sort of deep dive into vacuum tube voltmeters, or VTVMs, using the Heathkit IM-18 as an example. This picture shows a special version of the IM-18. This is the IM-18, which was a version made for the Advanced Schools Incorporated of Chicago. It was exactly the same as the IM-18 except for the silk screening on the front. So why did vacuum tube voltmeters exist in the first place? Well, it was to avoid loading down circuits under test. The older meters, just the standard VOMs, volt ohm meters, got all of their operating power, including the power required to move the meter pointer. They drew all that power from the circuit under test, and depending on what kind of a circuit it was, the circuit might not even notice it's being tested and power drawn from it for the meter, or the circuit might actually kind of freak out and work differently or not at all due to the loading presented by the volt ohm meter. So one of the first ways of alleviating that problem was to introduce a high impedance stage into the volt ohm meter by the use of a vacuum tube, and that made the vacuum tube voltmeter, or VTVM. Since the kind of vacuum tube used for VTVMs allowed the input impedance to be very high, that in turn allowed the front-end conditioning or pre-scaling circuits of the meter to have very high resistances, thereby presenting a high impedance to the circuit under test. Most VTVMs were limited by comparison to today's multimeters, whether they're analog multimeters or digital ones with solid-state front-end circuits. We're accustomed to these meters being able to measure AC and DC volts, AC and DC current, and ohms, and in many cases other things such as capacitance and measuring transistors and so on. But the traditional VTVM could measure AC and DC volts and ohms, and that was it. To use as an example for the discussions that I'm going to present, once again I'll be using this Heathkit IM-18 in the special IM-18 version, just so I have something to show while I'm talking about it. This is actually fairly late in Heathkit's lineup of VTVMs, which, as far as I can tell, started out around 1947 with a model called the V1, and that was replaced in turn with the V2 in 1949, and also a V3 from the same time period, and the V4 from 1949, and the V5A from 1951. These are all very similar. And then we're getting into the V6 and the V7 in 1952 and 1954. And by the time we get to the V7, Heathkit had pretty much designed the VTM the way they wanted it, and all subsequent models were really just repackaging of the same circuit in different shaped cases, or the same kind of case but with different paint schemes and silk screening. Some of these models post V7 included the IM-11, which was the first one that was really just like the IM-18 I'm using as an example. That came out in 1961 and was made through 1968, and that was followed by the IM-18 in 1968, and they made that model through 1977, finally replacing it with the IM-5218 in 1977. That was Heathkit's last VTVM model before they stopped production. Meanwhile, they also made several models of really the same thing but in a benchtop configuration, something that was intended to be sat on the bench, and it had a horizontal profile, but it had the same circuit and the same meter and the same knobs. So this discussion is going to cover all of those models. Just one more thing on the generic side of this. Heathkit was not the only company making VTVMs, of course. Just in the kits alone, there was ICO and Nightkit and probably some others. And then there were also commercial units made by some of the big name companies. And there's a lot of similarity in the circuit. They may have done some things a little upside down or backwards and so on, but the concept and the basic circuit was very similar between them. So the first thing I want to cover is how these are opened up. The Heathkit models that resemble the IM-18 all open up by simply removing 2 screws from the back panel on either side of where the power cord goes in, and that releases the case from the chassis, and the case, which is left in this photo, just pulls off, and you're left with the chassis as shown on the right. To get them really separated, you need to fish the power cord through the hole and pull it all the way separate from the case. Now here's an overview of the chassis. The way it's oriented in this picture, the bottom is at left and the top is at right. So the power transformer that's at the far right of the chassis in this picture is actually at the top of the meter. So on the bottom half, basically what we have is the input jack for the test probes. The earlier models in this series, going way back into the earlier V models, actually did not use a single jack. Instead, they used 3 jacks arrayed along the bottom edge of the front panel. But electrically, it's the same thing. So we've got the input jack, and then we've got the 2 rotary switches. The tall one is the range switch, and the short one is the function switch. And then everything above that is the circuit board. Right along the bottom of the circuit board are 3 potentiometers. Those are your calibration potentiometers, and they're accessible by screwdriver, just by bringing the screwdriver in below that metal bracket that has the power cord coming out of it. Alright, here is the chassis looking at the top side of it. At the far left, we have a tubular device of black color, which goes from the circuit board right up to the front panel. In this instance, somebody's put a little piece of red tape in there, but that's where the pilot light goes, inside that black tube. And the tube is made out of a flexible, temperature-tolerant fabric material, which prevents light escaping and also just protects the bulb and will not get damaged by the heat of the bulb. And the pilot light is really just to tell you that the power is on, because otherwise you may not be able to tell. And it is not there to illuminate the meter, as some sources claim. To the left of the pilot lamp is the power transformer. Its primary purpose really is to provide electrical isolation. It's nominally a 120 volt AC input, and its primary secondary winding, or its principal secondary winding, is also 120 volts. So in that sense, it's just an isolation transformer. But it also has a tertiary winding, and that is for the filaments of the vacuum tubes. It's a 6.3 volt winding, and it's really able to power just about 3 things, and that's the heaters of the filaments of the 2 vacuum tubes, and also the pilot lamp. There's just a little bit of reserve left over, which is often utilized by battery eliminators, which are retrofitted onto these by many users. To the right of the power transformer are basically 3 things. At the far right is a silicon diode. That's the only solid-state diode in the VTVM. And then an electrolytic capacitor, which is used as a filter. That diode and the capacitor are across the 120 volt secondary winding and produce a half-wave rectified and filtered DC voltage, which is used to power really all the circuitry in the VTM, not counting the tube filaments and the pilot light. The third thing is visible here really as two thicker white wires going to some brass screws, or you can see the nuts on the screws more than you can see the screws. Those are actually the terminals of the meter movement, which is behind the circuit board, and their two terminals poke up through holes in the circuit board. They don't actually make connection with anything on the circuit board. That's why those two white wires are coming in from elsewhere and going to terminals that are pinched between the circuit board and those brass nuts. So that's really the third thing in that area. And then finally we have that metal bracket that does two things. Once, it provides a strain relief point for the power cord, and it also provides the negative or the support for the negative battery terminal. And you can see that coil spring that's attached to a screw in the bracket, and that's what makes connection to the rear end of the 1.5 volt C cell. Meanwhile, the positive side of the C cell, what we're just going to call the battery here, goes into that aluminum cup on the circuit board, and that's where the positive side of the battery makes connection with a foil on the circuit board. And then, of course, on either side of that battery cup are the two vacuum tubes. The one on the left is a 6AL5, that's a twin diode tube. And then on the right is the 12AU7, that's a twin triode tube. So now I'm going to talk about the principal things that are likely to require restoration whenever somebody obtains one of these, especially if it hasn't been used for a while or it hasn't already been restored. These are things that I've always worked on any of these I've done, and I think pretty much everybody would agree they're things that should be done. So the first thing off is right out of the gate, you're going to change the filter capacitor. It's the only one, and in this photo it's the silver can that's just to the right of the transformer. This is a 16 microfarad 150 volt capacitor. These are pretty readily available, and you get them in the axial shape with one lead on the left and one lead on the right, as opposed to the radial kind, which is a little more common these days, but these axial caps are still readily available. The other capacitors in the VTVM are not really visible in this photo. One of them is another axial capacitor, a fairly large one, and that is your primary AC coupling capacitor used for AC volts measurements. And that's sort of tucked out of sight in this photo, but that rarely needs to be replaced. These are usually parts that just don't go bad unless they're physically damaged, so I've never had to replace one. They've always been fine. And all the other capacitors are just non-critical ceramic disc capacitors, which again tend to not go bad, and even if they drift a little bit in value, the values are not critical, so you most likely will not have to mess with those either. One thing that is almost certainly going to need some attention, especially if the meter hasn't been used recently, are the contacts on the selector switches. And in this view, the rear deck of the range switch is visible, taking up almost half the photo. And you can see the wiper ring on it is almost black with oxide. Those should be nice and shiny, and it's imperative that you get these working well, because if you're making bad connections on these switches, then you're not going to get good results from the meter. It's not going to work properly. And for this, I just use regular deoxit products. There's several different kinds, but their most common product, I think it's called D5. Or you can use any of the other brands of switch deoxit products. Uh, I spray it around, usually one deck at a time, and on this particular type of meter, the Heathkit VTVMs, the contacts tend to be on the rear side of the decks, like the one you see here, but on this series of meters, each of the two switches has 3 decks, and the deck closest to the front panel has both a rear and a front face to it. It's a little hard to get the deoxit in to the front face of the front deck, so you have to kind of get down there at a low angle, but the idea is to give it a good squirt and then work the switch back and forth a whole bunch of times. I would say at least 20 times back and forth in quick succession while the deoxit liquid is still fresh. And then I usually do all the other decks one after another, and then also put a little blast into the potentiometers. There's 2 of those on the front panel, and then the 3 of them that are on the circuit board, and work them back and forth a bit. Some people say you should not use these deoxit products on carbon composite potentiometers, which is what would be used on this meter, but the preponderance of empirical data says that it should be okay. And certainly I've not had any products doing it myself, or any problems doing it myself. And I do follow it up with an air duster can to kind of blast the residual deoxit fluid out from the pots and the switches, and then just sort of, wipe up around it to get any little pools of the stuff that have gathered in various spots, and then let it dry for a bit before powering it up. Another thing is the pilot lamp. This is a 6.3 volt type 50 screw base incandescent bulb. It's really designed to be used as a pilot lamp because of its 6.3 volt design. You don't really find that voltage in flashlights and things, so it's really intended to be a pilot lamp. They're readily available and dirt cheap. The reason I suggest replacing them, even if they're working, is that they're a real pain in the neck to replace. And if you're in here taking the meter halfway apart anyway to do other things, you might as well replace the bulb while you're at it. And the way you have to do that is you have to get the circuit board a little bit free from the from where it's held in place. And in the left of this photo, you can see a metal bracket, sort of a Z bracket, that goes up from the front face of the meter to the corner of the circuit board. And then there's also the 2 screws, the 2 brass nuts that are for the meter terminals, the meter movement terminals, I should say. You have to loosen and remove those 2 brass nuts so that the circuit board can come free of the back of the meter movement, and also remove the screw that goes in through the mounting tab of the transformer into that Z bracket at the left of this photo, and that allows the circuit board to lift up enough that you can slip that black sheath off of the bulb, unscrew the bulb, put in the new one, make sure it's in there tight because it's harder to tighten up later, and then reverse the whole process. Put the sheath back on, put the screw through the transformer into the Z bracket, and then return the 2 brass screws to the meter binding posts, making sure to put the 2 white wires and their solder tabs under the brass screws before you tighten them up. So once all those things are done, and here you can see a new capacitor for the filter cap has been soldered in. And now I'm going to address the battery eliminator. The single C cell, which is used as the battery, if I'll use the term loosely, is really only applied when you're in the ohms mode. It's not used otherwise. But to clear up one bit of confusion about these, I've seen some people say, well, because of the battery, the VTVM can be used without being plugged into the AC power, and that's not true. The bulk of the meter's circuitry runs off of the power derived from the power transformer, and that battery, that C cell, is only used to provide an excitation voltage while in the ohms mode, and it has nothing to do with running the rest of the meter circuit. So you do need to have the meter plugged in, but if you're going to measure ohms, you also need to have something to provide 1.5 volts and pretty stably 5 or 1.5 volts, or you're going to have problems with the resistance or ohm meter functionality. The other thing about the battery used for the ohms function is that, especially when you're in the lower ohms ranges, the ohms circuit takes a lot of current, and it can deplete the battery fairly quickly, or at least drop its voltage enough that you're having to mess with the adjustments a lot more, and it becomes a pain. And the manual actually strongly suggests that, especially when you're measuring the lower ohms ranges, that you take your reading and then remove the test leads from the resistor or resistance under test as quickly as possible to avoid depleting the battery. So once again, that's sort of a pain in the neck, and you could certainly kill the battery by leaving the VTVM in the ohms mode and connected to a resistance under test for an extended period of time. You know, you go off and get lunch or something, and you'll come back and the battery will be dead. And if you keep leaving it that way, you can encourage the battery to leak, because especially with alkaline batteries or alkaline cells, their biggest cause of leakage is when the battery gets depleted past a certain point. So it's a good idea, really, to put a battery eliminator in these meters. Heathkit themselves is reported to have modified all of their own VTVMs that they had in their own design and testing labs with battery eliminators. And these days, with simple solid-state voltage regulator chips, there's almost no excuse to not put a battery eliminator in these VTVMs. I have a video I did a few years ago on another IM-18 that I own about hacking it to put in a very basic battery eliminator. And while that works, I certainly got my share of commenters saying it wouldn't work, or it wouldn't work well, or while it worked, it would stress the power transformer, or this or that. It turned out that that was the basic design that Heathkit used on the VTMs that they owned, so I don't think it was that bad. But anyway, it seems like the general consensus is it's better to do it with one of these LM317 type off-the-shelf voltage regulators, which can be easily pressed into service as battery eliminators. And this is just a screenshot from eBay showing one of them that seems to be quite popular. So the one I'm going to show in my subsequent discussions is this one. Back to this photo again. A battery eliminator of the type I'm discussing needs to be mounted to the circuit board, and the kit that I've been buying from eBay comes with two nylon, I think they're nylon, insulating spacers and screws so that you don't short anything out inadvertently with them. All you have to do is drill 2 holes in the circuit board, and this position on the board is what the seller recommends and what I found to work best. It's an area of the board where there's not much in the way of foils on the other side, so it's easy to find places to put the holes without disrupting something. And here's that battery eliminator mounted on its nylon spacers with some nylon screws. The parts that the seller on eBay is included are the wires coming off the yellow, the blue, and the green wires. And then not shown in this picture because it's on the back side of the battery eliminator is a diode and some clear shrink wrap tubing for an insulator, and that's the rectifier. and then this electrolytic capacitor that's sticking out the terminals on the left side of the battery eliminator. That's the filter capacitor that's used to provide a smoother power into the battery eliminator circuit. So the eBay seller of this particular battery eliminator gives installation instructions, but they're pictorial in nature, so it just has some small color photos of a typical VTVM and says, you know, connect the yellow wire here and the green wire here and the blue wire there. When I followed those instructions, I found out that while the battery eliminator worked in and of itself, it was conflicting with the grounded versus the non-grounded side of the filament circuit in a way that kind of squirrely threw off the ohms function. Even though it basically worked, it was sort of non-linearly spastic, and it just didn't work correctly. And I'll discuss that again here in a moment. So this was the first time I'd used this particular battery eliminator kit. I'd built a couple of my own design on some other ones, and also used the more primitive one on a couple of VTVMs that I'd restored in years past. But this particular one, once I found out that there was a problem with the installation instructions, I rewired it as shown here. I think it's easiest just to tack the green and yellow wires onto the solder tabs for the pilot lamp as shown here. You don't need to snake the wires through holes and things. Just put a blob of solder on each of those two tabs and then stick the wires on. The left side of the pilot lamp, as shown in this photo, is grounded to the chassis, and the green wire from the battery eliminator needs to go to the grounded side of the circuit. So you want the green wire on the side of the lamp towards the transformer. But this is not to say that some other VTVMs, maybe even some of the Heathkit ones, may have the right side of the lamp being grounded. So this may not be a solution that works for everything, but it certainly worked in the case of this IM-18. And then meanwhile, the yellow wire, which is the voltage input to the battery eliminator, needs to come from the ungrounded side of the filament circuit, which is the right lamp terminal when viewed from this orientation. So that is why the green and the yellow wires are going where they're going in this photo. The third wire on the battery eliminator is the voltage output, and that's the blue wire in this picture. It gets snaked around and then fed up past the vacuum tubes and over towards the range switch, where it finally gets tacked onto the switch terminal on the rear deck of the range switch. This is the same terminal that has a 9.1 ohm resistor going to it, and also a blue wire that comes ultimately from the battery plus terminal. So what we're really doing here is connecting the output of the battery eliminator to the same point in the circuit that normally would get the plus of the battery. Now with the battery eliminator fully installed and wired up, it's time to make sure that it produces the correct voltage. For this step, you can have the vacuum tubes installed or not, it doesn't matter. You just need to have the VTM plugged in to AC power and turned on. And you can see here that I have the points of a multimeter touching the terminals for the voltage output of the battery eliminator. And then I'm going to look at my multimeter, and out of the box, this particular eBay seller states that they adjust it a little bit high to somewhere around 1.6 volts, and that's indeed what I measured. So then I used the small trim pot on the battery eliminator to dial it into just a little bit over 1.5 volts, so closer to the nominal voltage you'd get out of the normal battery. What about the vacuum tubes, you may ask? Well, I have generally experienced that the tubes in this particular type of VTVM design tend to last an awfully long time, seemingly forever. But sometimes you do get a bad tube or one that's just underperforming a little bit. And on this particular one, I found that both of the tubes were seemingly not quite right. So I ended up buying some new old stock or NOS tubes on eBay from different sellers. The first one I'm showing here is the 6AL5. That's the twin diode tube. It's really two diodes made out of a vacuum tube inside one package. It seems from my experience that 6AL5 tubes, although I thought they'd be kind of rare and hard to find, I had no trouble finding sellers with these as new old stock as opposed to ones that had been pulled out of equipment and tested, or just pulled out of equipment and assumed to be working. There seem to be a lot of sellers with new old stock at reasonable prices. So I wouldn't say that should be a problem for most situations. As for the 12AU7 twin triode tube, I had a little more trouble finding exactly what I wanted, at least on eBay. There were certainly plenty of people selling 12AU7s, but often they were selling a whole batch of them, which made it more expensive, or they were selling ones that they couldn't say for sure if they were working or not. I finally found one seller that had a number of tubes from the National brand, which, as near as I've been able to tell, is sort of a catch-all brand of generic tubes that could be sourced from all sorts of places. The particular 12AU7s I got were actually sourced out of, I believe it was East Germany, based on the markings on the tube. And doing a little Googling, I saw a number of people claiming that these were junk, but I've had a lot of experience with Nixie tubes that come out of the former Soviet Union and also East Germany, and I've had very good luck with those, so I'm not too worried about it. But having said that, there's a lot of advice from various other people who do restorations, and there is at least 3 other models of tube which are apparently more readily available and tend to be less expensive than the 12AU7, and which purportedly will work just fine in these VTVMs, and that's the 12AT7, the 12AV7, and the 12AZ7. So again, I can't endorse those, but that's what I've heard. Usually when you obtain these VTVMs, they do not come with the original test leads. Heathkit in particular, at least on the majority of their models, used a combination test lead that had a common wire with an alligator clip and then a shielded wire that went to the probe with a switch on it that you could use to select whether it was being used for DC voltages or AC voltages and ohms. That type is almost unobtainium. If it doesn't come with a meter, you're probably not going to find one. They weren't all that well engineered. They tend to break, and they're pretty much unrepairable, so there aren't that many of them, I think, that are still available, and it's not probably worth messing with. There are sellers, and I'm going to show here the brand that I routinely use on all the Heathkit VTVMs and early solid-state voltmeters and multimeters. They all take the same type of modern test leads. And here is the seller I buy them from. This is the eBay listing. It's high-quality parts, so I'm not trying to endorse only this one seller, but this is the one that I use. Alright, here's where I'm at on this. I've just replaced the vacuum tubes and rewired the commercially available battery eliminator to the correct wiring, not the one they describe in their instructions. And I've given it about 20 minutes to warm up, so I'm going to see if I can calibrate this guy now. Using the DC probe, that's the one with the 1 meg resistor inside of it, connected up to my bench power supply, which is set to 5 volts. And I've got it in the 15 volt range. Well, I'm going to put it in the 5 volt range. Making sure the meter looks pretty zeroed. Looks a little low to me, but I already zeroed it, so the zeroing at this point is dependent on the zero adjust here, not this guy here. So I go and crank it up slightly. I can move it around, get it close to 0, turn on the power supply, and I'm getting a nice full scale reading. No problems. So the DC cal is correct. If I wanted to calibrate it, I would just adjust that middle trim pot there on the circuit board. That's the DC cal pot. But in this instance, it does not require any adjustment. But let's mess with it anyway. So I'm fiddling with that pot right now. And I've got it set to just about exactly where it needs to be. AC and DC volts on this meter are read off of the same scale, and that's because the circuit is calibrated to allow that. So it's either going to be a number with a 5 in the most significant digit, or a number with a 15 in the most significant digit, or digits. So there's always this parallax I'm looking at here. Now it seems like it's reading a little low, but I'm kind of cheating here by trying to adjust this when the meter isn't completely warmed up. And so I have the test leads shorted out, and I'm verifying I'm getting a reading of 0, pretty much. These things are always a little drifty, so you have to adjust the 0 adjust with some frequency. And if all is perfect, going back and forth between the DC plus and the DC minus should result in minimal meter deflection. Ideally it should hardly move, but it's not uncommon for it to move slightly. So you can fiddle with the zero control like I've got it in there now, where it's just the slightest meter movement going between DC minus and DC plus, so that's properly zeroed. And then unplugging the test leads, if I go to the AC position, that's a pretty big deflection. Okay, here's adjusting the AC balance. Should be getting it to right about 0. And when I go back and forth between there and DC minus and DC plus, the meter shouldn't move much. The AC balance was not working consistently when I started shooting this video, and I found out that the center lug of that pot had a really crappy solder joint to the circuit board. So I had to pull the whole thing apart, kind of hard to get at it. But now it seems to be working. That's a good thing. Alright, I have the test leads back in, and they're connected to my AC access panel, which is set up to my variac, which is currently set to 100 volts as confirmed by my fluke. And I'm going to turn, I've got this set to 150 volts. There we go. So I should be getting it to be somewhere around here on the scale. So the AC cal pot is this one over on the right side of the circuit board. Alright, so it's right up to 100 now, so that's calibrated. And if I crank the variac down to about 50 volts, we should be getting 50 volts here. So that's working pretty well. That's all the calibration there is to do on these meters. Going to the ohms range, or ohms function, I've got it in the R times 1 range, and the test leads are open, and I'm getting a reading of infinity. If I short the leads out, I need to zero the meter. So take it down to 0, open the leads up again, and redo the ohms adjust for a full scale reading of infinity. Short the leads out again, make sure that it goes back to 0. Okay, so now if I connect my resistor decade box, I'm going to dial in 5 ohms. And I get a nice reading of 5 on the ohm scale. I'll go to the 10 ohm setting on my decade box, and I get right on 10 ohms. 20 ohms, 30 ohms, 50 or 40 ohms, 50 ohms. That all looks like it's right on the money. Let's go up to the R times 10 scale, and it goes off because I need to readjust it. So I start by shorting the leads, re-zeroing it, opening the leads, and using the ohms adjust to bring the top reading in, the full scale reading. Short it out again, verify it goes back to 0, and then connect up the decade box again. Okay, so now I'm going to put in 30 ohms on the decade box, and it's right on there. Let's go to 80, pretty much right on there, so that's good. If I go to 200 ohms on the box, it's pretty close to 20 times the 10 scale, so 200 ohms. Let's go to the R times 100 range. Check my 0 and full scale. The 0 is looking pretty good. Full scale is looking pretty good. So I'll give it 3K, which is giving me 30 approximately on the meter, times 100 is 3K. So that's looking good. Let's go up to the R times 1K or R times 1000 range. Check my settings. Full scale looks okay. Shorted looks okay. Reconnect the decade box. And I'm going to go to 1K. And it goes right up to there. 2K, 3K, 4K. That's looking pretty good. I'm going to go to 20K. And it's just about 20 on there, so that's looking good. And I'll go to 10K on here. Once again, verify my 0 and full scale. Looks pretty good. So I'll go to 300K. I've got 30 on the meter times 10K gives me 300K. So that's working pretty good. I can't really go any higher than 900K with my decade box, but it's just about in that position on the meter. So I think we're doing pretty good here. Let me just go up to the R times 100K and dial in 100, 200, 300, 400. Yeah, it's pretty much in the ballpark. And then go to the meg, R times 1 meg, and 500K should give me about half of that. It's a little low, but these are not highly precision instruments. So we're about in the right place. I would say all of the ohms functions are working using this battery eliminator. And I'm going back to the DC just to make sure I didn't mess anything up. That should be 4 volts, 3 volts, 2 volts. Yeah, that's tracking well. Alright, here's the original Heathkit schematic diagram. I'm not going to dwell on this version because, as usual, they were just jumbling things around to try to use as little space as possible. And they use this horrible thing that the way they depict the rotary selector switches on Heathkit schematics is just appalling. Unless it's the simplest thing, it's very hard to figure them out. You know, some of the things like a simple selector switch like this one, you can mostly figure it out. You can say, well, this is obviously the common, and it's got a longer contact that reaches all the way into this ring, and then it has shorter contacts for the 7 ranges, and there's one tab on the rotating part that can engage only one of the shorter contacts. So that one's real simple. But you get into some other things like this, where there's multiple long contacts and short contacts and multiple tabs and shapes, and it's very hard to picture in your mind what the contacts are. And I actually did this by using the photocopier to make like a 400 times zoom on some of these switch decks and make 2 copies, and then cut out the actual rotating part and then lay it on the other copy and mark off the degrees and move it to each of the positions to see what actually makes contact to what. And I wouldn't want anybody else to have to suffer through that. So I do what I often do, and that is redraw it in CAD. Make a rational schematic. So let's start with the power supply. We have the incoming AC line cord. The neutral is connected to the circuit board at a hole called line, and from there either 1 or 2 transformer primary connections are made by just soldering the wires into a hole that's adjacent to the hole where the line cord goes into. In the case of the 120 volts, it's these 2 wires, the black, green, and the black, go to there. And then the hot side of the line cord goes up through the power switch, which is just one of the contacts on the rear deck of the function switch, which is closed in all positions except for the off position. And then that has the remaining transformer primary wires going directly to it. So when you close the switch, you energize the primary windings. Then we have this, I mentioned it earlier that this transformer is for the most part just a 120 volt to 120 volt isolation transformer that gives the meter, for most situations anyway, electrical isolation from the line voltage. But it's not a step down. So we have this 120 volt winding here. It's only rated for 10 milliamps, but the high impedance circuit it's running doesn't require very much. We also have another secondary winding. This is for the filaments of the tubes. It's 6.3 volts, rated for 80 milliamps. And that has yellow wires where there's the primary or the principal secondary winding has red connections. And all those secondary wires terminate to unmarked holes on the printed circuit board. One of the wires from the 6.3 volt winding is connected to chassis ground. And it's done through the circuit board, so the wire goes into the circuit board, then the circuit board trace goes around and eventually connects up to a pad that is connected to the chassis. And there's also, I think, a wire that makes a trip to the central grounding point, which is the common of the input jack. You also have the two filaments of the 12AU7 tube, the single filament of the 6AL5 tube, and the pilot lamp. Once again, a type 50 6.3 volt incandescent bulb. So all those things are on the secondary winding. And as I have a note here, if you're going to look at the battery eliminator, there's a note on another sheet of this drawing that talks about how to connect that up to this filament circuit. Going back to the principal secondary winding, we have a half-wave rectifier comprised of a single diode. It's a silicon diode. And because the load is very small on this, it only needs a 16 microfarad capacitor, but it does need to be rated for 150 volts or higher. Now, this is your V plus up here, and this is your V minus, but as these notes indicate, there is something that has to form your virtual ground, because the rest of the circuit after this point is sort of bipolar in the sense that you will have voltages going above and below the ground reference. And so that's partially established here. These resistors here, it's a 10K pot and a 10K pot and a 10K resistor, making about 20K, and then a 27K resistor. And those make a big voltage divider between V plus and V minus. And then you've got this low value 100 ohm resistor going to the circuit ground, which is also chassis ground. And throughout this schematic I use the chassis ground or earth ground symbol instead of the ground symbol that's more commonly used for circuit ground. And that's because I wanted to stress that the chassis and the circuit ground are the same on this. Which is not always the case. Anyway, so you establish a point that's roughly between V plus and V minus, and that is tied to ground. So that makes this point positive relative to ground, and this point negative relative to ground. And it can vary somewhat. The Heathkit schematic calls it plus 50 to plus 70 volts relative to ground, and this point minus 80 or minus 60 to minus 85 volts from ground. So let's look at the simplest thing, and that's DC volts. The probe on the pretty much all the VTVMs is done the same way, even with different brands. Most of them use a composite or combination probe, which has a switch on it, one switch position for DC volts, the other switch position for AC volts and ohms. The difference is whether or not a 1 meg ohm resistor is put in series with the probe tip or not. In DC volts it is, in AC volts and ohms it is not. And then the test clip for the common is just on a black wire that goes back to the ring of the phone type plug, and then the tip is coming from the probe tip. And then there is a 1/4 inch tip ring type phone jack with the ring tied to chassis / circuit ground, and the tip being connected here. There's the range switch here. This part of it's only engaged for AC volts, so let's follow it down here to another deck on the function switch. This is the front deck, front half. And whether you're in DC plus or DC minus position on the function switch, that signal just passes through and is presented to the top of the main or primary attenuator circuit. This has resistors 7 megs, 2 megs, 700K, 200K, 70K, 20K, and 10K, finally ending up at circuit ground. So if you were in the 1.5 volt range, for example, you would have all these resistors added up in series, and then the 1 meg resistor here as the top resistor in this voltage divider. Think of it as being right here. So almost all the voltage being measured from the probe will be dropped across the much greater resistance here. All of these, by the way, add up to 10 megohms. And then you've got that 1 megohm sitting on top. And assuming you're in the 1.5 volt range, then you're tapping off that voltage divider where the vast majority of the voltage drop is across the 10 meg part and only a little bit is across the 1 meg part. So most of the voltage is developed here, and you're measuring that from the wiper of the switch, and then through another deck of the function switch. This is the front deck rear half, and again, and whether you're DC minus or DC plus, it just goes straight through. And now we jump to the circuit board. Everything over here is point-to-point wiring on or around the switches. But now we jump to the circuit board here. This is a circuit board connector. And we go up and we go through a 3.3 meg resistor, and there's a bit of a filter to ground. And then we go into the plate, or I'm sorry, the grid rather, of the 12AU7 tube. This is a twin triode, so it's one triode and another triode. And because they're part of the same tube, they should be pretty well matched and sort of tracking each other. And the amount of voltage here controls how much this conducts from the plate to the cathode. So it's like a voltage controlled resistor essentially. And what's up here? It's the V plus. So we're controlling the amount of conduction or conductivity of this by this voltage. As my note here says, the voltage here relative to circuit ground of approximately 1.36 volts will result in a full-scale meter reading when measuring DC volts. And of course the full-scale reading depends on the setting of the DC cal potentiometer, which is further down in the circuit. Similar voltages at full scale will occur here when in AC volts and ohms. The final meter deflection depends as well on the settings of the associated calibration pots. Note that the voltage here can be positive or negative relative to circuit ground. Anyway, so then the current continues down through here and through this 150K resistor back to this point, which is V minus. So we essentially have V plus up here and V minus down here. We have a variable resistor and a fixed resistor, so it's like a voltage divider. and the voltage at the middle of the voltage divider, that's this point here, will be controlled by how much resistance this variable resistor has, and that resistance is controlled by the voltage coming in here, which is of course proportional to the input signal being measured. So that all rolls up to the voltage here swings up and down depending on what the voltage here is doing. So the voltage here tracks the input voltage that you're measuring. What about the other triode? Well, that side, the grid is connected to ground through a 10 meg resistor. Because of the very high impedance of this tube, this 10 meg resistor can be kind of ignored. I think it's there more to allow some filtering with this capacitor, which you wouldn't get if this point was just tied directly to ground. Anyway, you're basically holding this point at 0 volts relative to circuit ground. And if you have 0 input signal coming through all of this, then you'll have 0 volts here. So 0 volts and 0 volts. Both triodes are conducting the same amount, therefore they should both have similar voltages here and here. But look at this. The resistor down here is a bit higher. It's 220K. I haven't figured out the reason for that, but I'm sure it's just one of those things that they found empirically perhaps needed to be tweaked to get the best results. It may also skew it a little bit. I'll talk about this part down here, but because of the skewing of the circuit that can occur from this zero adjust pot, it may be that they found out it's better to bias the whole thing in one direction. But this whole thing here, meaning this triode and this resistor, this triode and this resistor, makes a bridge. So this is your classic bridge circuit here. V plus up here, V minus down here. 4 resistors, 2 in this branch, 2 in this branch. These and this are usually fixed values. These 2 resistors here are these 2 resistors. And these 2 resistors are the 2 triodes, with the left one being variable according to the voltage applied from the input circuit. So basically these act like voltage dividers. There's a voltage divider here between V plus and V minus, and a voltage divider here between V plus and V minus. If both of these resistors are the same, or if these two aren't the same, then the amount of resistance here to here relative to the ratio from here to here means that you can balance this bridge so that the voltage here and the voltage here are the same, and you can vary it from that point by adjusting this resistance, which of course is what happens with the left triode based on the input voltage. Well, how do you tell if it's balanced or not? Well, the classic way of doing it is to connect a meter across the bridge. So the bridge starts out balanced, and when it's balanced, the voltages here and here are the same. Therefore, this meter, which is set up as a voltmeter, is measuring the difference between this voltage and this voltage. If they're both the same, then no current flows through the meter and it reads 0. But if you set it up so this resistance here changes to make this voltage higher than the voltage here, then you have current flowing in this direction through the meter, and it's going to read positively or upscale. On the other hand, if you arrange this resistor so this voltage here is less than this resistor, than this voltage here, so this voltage is less than this voltage, now the current will go in this direction and the meter will try to read negatively. So essentially, if you start out by balancing this bridge, then by adjusting this resistance according to the input voltage, you can get the meter to read more or less upscale in most configurations. So what if you have this thing set up and 0 volts here from the input and 0 volts here from being tied to ground don't result in the bridge being balanced? So you have a different voltage here than you do over here, left or right side of the bridge. Therefore the meter's going to read something when it shouldn't be. It should be reading 0 when you have 0 volts over here. Well, that's what this circuit down here does. We have to have some way of skewing these two resistors so that one's a little bigger than it usually would be or a little bit less than it usually would be. And there's several ways to do that. The way it's done on here is you put a potentiometer across the bridge from left to right and use its wiper to the bottom of the bridge. So if this zero adjust potentiometer is in the middle of its position, you can think about it as a resistor here and a resistor here, and then a resistor here and the same resistor here. And those are essentially in parallel with these resistors, and we know that if you have two resistors in parallel and you vary one of them, that varies the overall resistance, and therefore it would change that part of the bridge resistance. And while you're increasing one side, you're decreasing the other because of moving this pot around. So that's the way we can skew the bridge, and by skewing it we can get it balanced. When you know you have 0 volts here, and you know that means you should have a 0 reading on the meter, you can adjust this until you get that, and then the bridge is balanced. Now there's one thing about this meter that I probably didn't touch on too much yet, is that it's possible to set the meter up so that its pointer is in the middle when there's 0 volts. And then a negative voltage will cause it to go left, and a positive voltage will cause it to go right. That allows you to track voltages that can be above or below ground. And that's probably why these resistors here are not the same value. I think it has to do with that. To facilitate being able to balance the bridge such that you can get a center reading on the meter when you have 0 volts here, instead of having a 0 reading on the meter when you have 0 volts here. There's enough leeway by the choices of these resistors and the adjustment of this pot to allow you to get a meter reading like this at 0 volts here. So I'm pretty sure that's the reason for this over here. It allows the 0 position to be somewhere other than the middle of the potentiometer, and they're giving you more adjustment in one direction than the other. Let's follow the rest of this through. I already talked about how you would connect a voltmeter from this side of the bridge to this side of the bridge in order to measure whether the bridge is balanced, and if it's not balanced, by how much. So the way you usually convert a meter movement into a voltmeter, if you just have the meter movement by itself, it's always an ammeter. But if you put a resistance in series with it, and then measure from one side of the resistor through the meter movement to the other side of the meter movement, that makes it into a voltmeter. And that's exactly what we have here. We have from this side of the bridge a resistance, and then the meter movement, and then through all these switches back to this side of the bridge. And therefore we can measure the voltage across it. And to make sure we get the right amount of deflection on the meter for a certain voltage differential from here to here, that's why this is a variable resistor, and indeed it's the DC Cal potentiometer. So you just tweak this guy up and down to calibrate the voltmeter comprised of this and the meter until it reads exactly where it should be for a certain voltage from here to here. Now all these contacts here are actually part of the secondary deck, or the second deck. That's what Heathkit calls it. It's the middle deck of the function switch. And they're drawn this way because it's a crazy switch, and there's no way I could depict it for example, like this, and have it make any sense. And I already discussed why trying to just show it with the actual picture of the contacts and the wiper would be very hard to decipher. So I've broken it up into a bunch of discrete contacts which only close in one position. Like this contact is only closed in DC plus, this one DC minus, this one AC, this one ohms, and similarly over here. And because of the way the switch is laid out, some of these points are the same point. So for example, this is switch terminal 4, and so is this. But this is the one the wire goes to, the way I'm drawing it anyway. So you can think of these both being the same contact on the switch. And you can think of this to this being the same contact point on the switch. These two are the same contact point. These two are the same, these two are the same, etc. But drawing it this way makes it a lot easier to trace out. So let's say we have the function switch in the DC plus position. That means this one's closed and this one's closed. We come off the side of the bridge here, go through the DC cal resistor. We go through this closed DC plus position into the plus side of the meter movement, out the minus side, and well, we can't go there, that's the DC minus. We can't go there, that's the AC. But we can go through here, that's the DC plus, and then back around and ultimately to the right side of the bridge. So with all of this convoluted stuff, we just have this resistor and this meter connected from here to here on the bridge. What if we were trying to measure a negative DC voltage? Well, everything would be exactly the same as I already described, except the voltage would be negative relative to ground. And that means the voltage here would be negative relative to ground, and therefore that's going to cause this triode to conduct even less than normal. Remember that it's nominally set up to balance the bridge if you've got 0 volts and 0 volts. And going positive unbalances it in one direction, but going negative here unbalances it in the other direction. So now we're getting an increasingly negative voltage over here, and that causes this voltage to go lower than this side of the bridge. That wants to cause the current to flow in this direction instead of this direction. Well, that's going to cause the meter movement to try to go more to the left than it can go. So let's follow this through. This side, which is, well, we know that this side is a higher voltage than this side now, so let's presume current is flowing in this direction. So let's start out by going down here, we come back around, we go up here, we go through the DC minus contact, and now into the plus side of the meter. We want current to go from the plus to the minus, so the current's flowing in this direction. It flows out the minus side, and now through this DC minus contact, back through the resistor to this side. So that's how the function switch has reversed the polarity of this meter movement across the bridge. So now you'll get a positive or an upscale reading even when you have a negative voltage being measured. So what about AC volts? Well, in AC volts, we are using this voltage divider in the range switch, but we're using it in a slightly different way. And that's because we have to rectify the AC signal before it's applied to all this stuff that's expecting a DC signal. So we come in through the probe tip, because the switch is going to be selected to AC ohms. We go this way and bypass this resistor. We don't need it the way we're using the attenuator in AC volts. And that continues on through. And now, because the function switch is in AC up here, we have a path to go through. Meanwhile, if it tried to go this way, the signal can't get to here when the switch is in the AC position, so it's blocked down here. So the only way the signal can get through is through this deck of the function switch. This is our big AC coupling or DC blocking capacitors, so we strip out any DC component of the signal being measured, and it's applied to these three resistors back to circuit ground. If we're just in the 1.5 volt, 5 volt, 15 volt, 50 volt, or 150 volt positions, the switch makes this contact. It's only when you're in 500 volt range that you use this contact, or 1500 volt range that you use this contact. So we're just tapping off the top of this voltage divider, this pre-attenuator, when we're in, for example, the 1.5 volt range. So it just looks like a resistor load, but it's a pretty high value. And so we go straight through it, and once again there is a capacitor here, and there's a diode formed of this half of the 6AL5 twin rectifier tube, and then another diode, and then a capacitor, and then you come on out. I'm going to talk about how this works separately, but for now we'll just regard it as a rectifier and voltage doubler circuit. So it's going to rectify it, and then it's going to take the rectified voltage and double it, and that's what's going to come out of here. The reason we're doing that, in a nutshell, is that when we rectify something, we take only half the waveform. But we're trying to measure from the top to the bottom of the waveform, in other words, peak to peak. So the way we do that is we measure half the voltage by virtue of the rectifier, and then double it to get the peak to peak voltage. And it's also filtered by this capacitor, so because even though it's a very small value capacitor, because of the very high impedances out here, there's essentially no loading. Therefore, this can act as a filter capacitor and give you a nice, steady DC voltage here that is proportional to the peak-to-peak voltage of the incoming AC waveform. And then that is fed back here. Oh, also, because of the way this circuit here works, the voltage here is a negative DC voltage, proportional to the peak-to-peak voltage. We come back through here through another deck of the function switch. It's in the AC position, so we sail right through. And now we apply it to the same voltage divider primary attenuator that we did for DC volts, except now we use this side of the switch instead of this side of the switch. So why don't we need that 1 meg resistor up here? Well, to make this work properly, we need the ratios to work out, and by virtue of what's going on up here, in a way it sort of performs a similar functionality. It boils down to is you don't need the 1 meg resistor because you sort of have this instead. Anyway, so assuming again we're in the 1.5 volt range, you don't attenuate anything here, you just drop the signal across this 10 meg resistance, and then we come on out through here. We go through yet another deck of the function switch. It's the AC position again, and we come through, and this DC voltage is applied up here. But remember, it's a negative voltage coming out of this circuit, so we have to treat it the way we would treat the DC minus. And because of all of this up here, we need to calibrate it differently than we would DC, so it has its own resistor in series with the meter movement. That allows you to separately calibrate it from DC volts. It's in series. We go through the AC position, and it goes into the minus of the meter, just like it did for minus DC. Then we flow out the plus side of the meter, we come back around, and we go through the AC here, and return to the right side of the bridge. So that's how we get the meter movement to be able to accept the negative voltage coming out of the rectifier doubler circuit and still give us a upscale meter reading. And again, because it's a somewhat different circuit out here, instead of 1.36 volts here for a full scale reading, you're going to have maybe something a little different, and you need that to give you a full scale reading. And so then you just adjust this potentiometer here until you get that. And then the rest tracks linearly. Well, why are we doing this pre-attenuator if we're not going to use it? As I mentioned, on almost all the ranges, the 1.5 through the 150 volt range, we don't even use this pre-attenuator. We just sail right on through the rectifier, doubler, and then the primary attenuator and go on to the meter movement. Well, this tube here is only good for voltages up to around 400 volts. That's its maximum. So when you do get into these higher ranges, like the 500 volt range or the 1500, you have to divide the voltage down. You have to attenuate it before it's even presented to this rectifier tube. And so that's exactly what it does. If we're in the 500 volt range, we attenuate the signal and then apply it to the rectifier doubler and then go on through, but it's already been attenuated here, so we don't want to attenuate it again here, or at least not by as much. So that's why when we're using the right side of the function switch, which is what we do for AC volts, the 500 volt range here does not go to its corresponding point on this attenuator voltage divider. Instead, it's just jumpered up to the same point as the 150 volt signal. So we get less attenuation here, and that's compensating for the fact that we have some pre-attenuation up here. And the same thing for 1500 volts. If we're in 1500 volts, we take an even bigger attenuation up here, keeping the voltage again safe for this tube, and then attenuate it less at this stage, and it all comes out the same in the wash. There's a little nuance to the way the AC volts function works. These vacuum tube rectifiers are imperfect rectifiers. They apparently allow a small amount of current to flow in the reverse direction, and it tends to skew the results of the output, where it tends to be remembering that this is supposed to provide a negative voltage. It can cause it to be perhaps a little more negative than it should be to truly represent the input, and it's a constant offset having to do with the reverse leakage through the rectifier tube. So we need to do some way to bump this up a little bit to compensate for it being offset in the negative direction a little bit too much. And that's where we pick up here. There's another voltage divider. Well, it's the same voltage divider we have, which establishes the circuit ground at a point between V plus and V minus. But we can tap off of one of those resistors, because one of those is actually the AC balance potentiometer. We can tap off a voltage that's closer to V plus than it is to V minus by a fairly small amount. And then that's fed through all these resistances here, 4 22 meg resistances in series, and Heathkit calls that the buck out signal. And that gets mixed here with the voltage coming out of the rectifier doubler. Remember, this is a minus voltage, so we push it a little bit in the positive direction. And that's a one-time adjustment you make. You just dial out the characteristics of this tube and end up with a negative voltage here, which really is proportional to the AC voltage being measured without the offset being dialed out by this buck-out circuit. So what's left here? The ohms function. So there's lots of ways to measure resistances on multimeters. Some are a lot more sophisticated than other ones. My preference is to do it the way that modern digital multimeters do it, which is to have a circuit that provides a constant current and then feed that through the resistor under test. And because the current is constant, then just doing Ohm's law on the circuit, you'll have a resulting voltage drop across the resistance under test, which is proportional to the resistance value, and therefore it's linear, and you can present that directly to a voltmeter circuit, and you get a nice linear ohms reading. But on a lot of these simpler circuits, especially any of the purely passive old-fashioned VOMs that took all their power from the circuit under test, at least for volts and so on, and including these VTVMs, it's pretty universal that we're not going to have a constant current source. It's too complicated and expensive to produce. So we just do a very simple ratiometric circuit. So what we have here essentially is you have a built-in excitation voltage source. That's the 1.5 volt battery. It's really a cell, not a battery, but we'll call it the battery. And that is presented through a choice of resistances depending on the range switch. So let's pretend that we're just in the R times 1 range. So what we see is what we get essentially. It only has a 9.1 ohm resistor. So we don't even care about the rest of these. And they don't go to ground. You just add up however many of them go from here to the point where you're tapping off at the switch. So as you go to higher resistances, you add more resistance here. So we come out of the battery, we go through this 9.1 ohm, we come down here, and we go to this terminal, and we double back. We go through the ohms position on the function switch here. We go out through the test probe in the ohms position, so it's bypassing this resistance. You wouldn't want to have this 1 meg resistance hanging out there when you're trying to measure resistances. It would totally throw everything off. So we come out of here, we go through the resistor under test, which is connected between the probe tip and the test clip, and we come back in and it goes to circuit ground. So what we have is a battery here, and we go through some resistance. That's depending on which resistor or resistors here we have selected from the range switch. Then we go to the positive test probe. Then we go through our resistor under test, Rx. Then we go in through the negative or common test probe, and that goes to circuit ground, which is also where the negative side of the battery goes. So we essentially have that. This happens to be circuit ground, but we have a loop here. It's a simple voltage divider with the fixed resistor at the top and the presumably variable resistor under test on the bottom, and that causes a certain amount of current to flow through this loop from the excitation voltage of 1.5 volts. The voltage drop across here depends upon what this resistance is, but because this is not a constant current source, in other words, the current here will vary depending on what this resistance is. You can tap off. Remember, we're measuring to ground, so we can tap off here, and the voltage from here to ground will vary according to the resistance here. And by keeping this resistance fairly close to the general value of this resistor, we can keep this voltage within a fairly small window of possibilities, and that's what's necessary to drive into the balanced bridge circuit. So as this resistor under test gets larger and larger, we need to have a larger and larger resistance up here to keep this point within a certain range, and it can't be higher than the battery voltage anyhow. But that's really all that's happening here. But again, this is not going to give you a linear scale out here. So this requires that the meter scale be scaled in a non-linear fashion in order to get the pointer at a place that represents the resistance under test. So how do we tap off that resistance under test? Well, we already know that this point down here, coming off the fixed resistor, doubles back and goes out through the probe to the resistor under test. So this point here is the point where we're measuring the voltage that represents the resistance. And of course it's closed in the ohms position, so we can just read that voltage drop directly off through the balanced bridge circuit, just like we did for the other AC and DC volts. And of course it has its own calibration pot. But we don't call it a calibration pot here. It's a front panel control. It's not something you set only during meter calibration. It's something that's a working adjustment that has to be frequently adjusted. But electrically it's doing exactly the same thing. It's going from this side of the bridge to this side of the bridge via this resistor and the meter movement. So we go through the ohms adjust pot, we go through a contact that's closed in the ohms position, we go up here, we go through into the plus side of the meter movement, and then out the minus side, and we have to find a contact that's closed in ohms, and that's this one, and that brings us back to the right side of the bridge. Because the battery only has one polarity, we know that the voltage presented up here is always going to be positive. Therefore we know that the current through the meter has to be going from this side of the bridge to this side of the bridge. So there's no need for the function switch to reverse the polarity of this meter. It's going to be going from this side to this side, from plus to minus through the meter. Somebody might ask, why is one side of this filament circuit connected to circuit ground? Why does it have to be? Well, apparently the answer is that it does not have to be, that if you remove this ground reference here, the meter would still work. But this is a trick that they found out, that it makes the meter less susceptible to interference and electromagnetic fields and things if one side of this is connected to ground. So that's why that's there, but that can cause problems with various things, and I won't get into that level of, going down the rabbit hole, but depending on various modifications you might make to the circuit or various other things, that's something you have to keep in mind, that one side of that filament is filament circuit's connected to chassis ground, which is the same ground as the circuit ground for the rest of the meter. Especially when measuring AC volts, where you may be measuring something which is directly tied to the AC line voltage. Maybe you're just measuring the voltage at an outlet. Well, that's clearly line voltage. The meter's being powered by line voltage, and while it has an isolation transformer here so that no part of the balanced bridge circuit is connected to the AC line, you do have the ground lead of the power cord going to chassis ground, and that is also circuit ground, which means it's also the ground point or the common of the test leads. So let's say you went and connected this test clip up to one pin on an AC outlet. What if that pin is AC hot? Now you've essentially used the meter, its internal wiring, to connect AC hot to ground. Well, we know that's going to blow fuses and cause other things, so that's a big gotcha right there. You don't want to be setting it up so that you're inadvertently grounding a hot AC line voltage and blowing up something in the meter, or popping a circuit breaker, or causing other issues. Now, if you had it the other way around, where the black lead of the black test lead, let's call it that, is connected to neutral, which is bonded to ground anyway, and you use the probe tip to go to AC hot, well, then the meter's probably okay with it. You might still get some irregularities because the voltage at earth ground and the voltage at the neutral point on an ACL, it might not be exactly the same, and you could have some small issues there. But good practice and really safe practice when using a standard VTM, when they're all done the same way, is to, if you know you're going to be measuring into an active line voltage connected circuit, is to remove the ground. Use a plug adapter so that the ground is not made here. Therefore, the chassis and the minus terminal are not connected to ground, and therefore you can measure across an AC line connected voltage without causing that inadvertent path back to ground. However, you would really like your meter chassis to be grounded most of the time for safety, and so you don't want to be doing that very much. Another way to do it is to put the circuit under test, if you're able to, through an isolation transformer while you're working on it with the meter, and therefore there's no path back that way. But if the device under test also has its chassis connected to AC ground, irrespective of an isolation transformer, then you could still have the same issue. So really the easiest way to fix that is by making sure the VTVM does not have a ground path from circuit ground back to earth ground while you're testing AC line voltage connected circuits. Here's sheet 2 of my 3-sheet CAD drawn schematic and documentation package for the Heathkit VTVMs. On the left side, I basically do a bunch of sample circuits, leaving out all the switching but showing the resistances. I give a couple of case studies for DC voltage measurement, a couple of case studies for AC voltage measurement, and 3 case studies for ohms measurement, and have little descriptions and some math in there to describe how it all works out. Now, I also have a detail here on how the rectifier doubler circuit works, so let's go through that. This here is just a redrawing of what happens in the circuit right here. We have a capacitor coming in, a diode pointing at ground or circuit common with its cathode pointing down, and then another diode with its cathode pointing up, and its anode, which is equivalent to the plate, being connected to ground through another capacitor which has the same value as this capacitor, and then you get a DC voltage out of here. So redrawing that for simplicity using just regular diode symbols, it removes some of the confusion. So this is essentially what we have. This is an AC voltage input and a DC voltage output. And this here is a very classic circuit. I've even notated as such. It's known as the Greinacher circuit, named after Heinrich Greinacher, who invented this type of voltage doubler rectifier in 1913. So it's been around for about 100 years at this point. So I'm going to break it down into what happens on the positive half cycle of the AC wave and what happens on the minus half cycle, or the negative half cycle. On the positive half cycle, and I put this half of a sine wave here just to reinforce that, we essentially have a positive voltage here. And we have this capacitor here, C3, and because this diode is forward biased for positive input voltages, it can be treated like a short circuit, which is the way I have it here. So you essentially have C3 connected through the diode and back to the minus side of the V input. That places C3 directly across the input voltage, and it's going to charge up to whatever that voltage is. Meanwhile, we have C4, and its diode that would usually go through here is reverse biased when you have a positive voltage here. Remember, a positive voltage here causes a reverse bias on this diode, so it's open and you could just pretend like it doesn't exist. And that leaves C4 connected to the output voltage, so whatever voltage is on here based on its charge is presented to the output circuit, which is the primary attenuator and the balanced bridge circuit. So the bridge is, during the positive half cycle of the AC signal being measured, the meter is measuring whatever charge happens to be on C4, and meanwhile we're charging up C3 to equal the input voltage. But remember, that is because of the fact that you've got a forward bias diode here. So it's only allowing that charging to occur when the diode is forward biased. In other words, on only half of the input waveform. Therefore, the rectification happens right here. Now let's look at the effective configuration when the input is in the negative half of the wave. It's a minus input. So you can picture that as if it was a little battery connected out here that has a voltage equal to the peak of the minus half of the waveform. And its positive, therefore, is down here. So the polarity is flipped because it's the minus half of the wave. But C3 still has its charge on it. So the diode that was formerly forward biased is now reverse biased and therefore is shown as an open circuit here. And the diode that was formerly reverse biased is now forward biased, so it's shown as a short here, just as a piece of wire really. And what does that mean? We have a voltage across here with the positive down here and the minus up here, which is the input voltage, and it's in series with a capacitor that has the voltage from the positive half wave across it, and their polarities are plus to minus, so they're in series with each other. So you essentially have the stored voltage from the positive half cycle of the wave and the voltage of the current minus half cycle of the wave in series, so you get the entire peak-to-peak voltage from having these two in series, and those are presented in parallel with C4, so it charges up to the minus polarity peak-to-peak voltage of the input signal, and that is presented the output. Then the AC flips back to positive and we get this configuration again. C4 is left on its own with this voltage acquired in this step, and again that's a DC voltage which is proportional to the peak-to-peak voltage of the AC waveform. So that is constantly presented to the circuit going out towards the balanced bridge. And that is how this circuit acts as both a rectifier and as a voltage doubler, with the voltage doubler necessary to give us the peak-to-peak voltage rather than just the peak voltage. And because this VTVM is a peak reading meter, first and foremost, you do want to be looking at the peak-to-peak voltage, not the average voltage. However, the meter does have a scale which allows you to read the AC values as an RMS if you need to do that. And of course the RMS is going to be, at least for a sine wave, it's going to be what you will see on most other kinds of meters. So it's useful to have both the peak reading and the average reading ways of measuring AC signals, and this meter does provide it through just having differently scaled meter face. Okay, the battery eliminator. I included that here because I think so many people are going to do it, want to do it, whatever. And there's a lot of balderdash about battery eliminators out here. I've already mentioned earlier that I've successfully built, and even Heathkit successfully built, very simple battery eliminators that did not require integrated circuits or active components. Just a resistor and a diode or two or three and a capacitor. And those do work. It's important to get the resistance values right so you don't throw off the functionality of the ohms meter. But they do work. However, you can do it nicer than that. So I'm only talking about doing it with the IC in this case. And the LM317 is certainly the most common way of doing it. So we start out with the available low voltage. It's already here in the form of the 6.3 volt filament circuit. And we're going to use very little current here so the filament circuit can provide that little bit more. But keep in mind that it can increase, I think the worst case, as I figured out here, is 165 milliamps. Well, what's that mean to us, right? We're stealing up to 165 milliamps in the lowest R times 1 range of the ohm meter. So the ohm meter circuit draws the most current from the battery or from the battery eliminator when you're in the lowest range, R times 1. And assuming that the Rx, the resistor under test, is 0, you can draw as much as 165 milliamps. Well, Heathkit says that the 6.3 volt filament winding is only rated for 80 milliamps. So how does that work? Well, it works for a couple reasons. One is that just the fact that the transformer secondary is rated for 80 milliamps doesn't mean it's going to drop dead and roll over if you pull more current out than that. It's also based on the presumption that you're not going to do sustained readings. You're going to take a reading for a few seconds and then disconnect the test leads. And also, most of the time, you're probably not going to be measuring in the lowest ohms range, and the currents will be a lot lower. But you will find situations where you potentially have less accuracy in the ohms function if you're in the lowest range, just because you are pulling so much current out of the battery or battery eliminator. And therefore you are stressing, if stressing is the right word, you're drawing more than the nominally rated current out of a winding, which by itself is already designed to provide current to the heaters or the filaments and the light bulb, which themselves probably draw about 80 milliamps. It's not over-designed, so you're potentially drawing 3 times as much current out of the, or twice the current out of the secondary winding as it would normally provide. But, you know, if you're going to keep doing that, you're probably going to get to a point where the transformer is going to get warm, and certainly the voltage on the filament circuit will drop a little bit because it's not designed, the transformer is not designed to be putting out that much current on that winding. But it's not like it's going to go to 0, it's just going to go to something a little bit less than 6.3, and the transformer probably will get a little bit warm. So that's a caveat. Anytime you do a battery eliminator tied into the filament circuit as its source of power, and when you're working in the low resistance ranges, it's not a problem really. The higher the resistance range, the less current you're pulling, to the point where if you are, for example, in the 10K range, which is not an unreasonable range to be in for measuring a lot of electronic things, you're already down in the microamps that you're pulling out of the filament circuit, or out of the battery, depending if you're using a battery or the battery eliminator. So with that out of the way, let's just say we're not going to worry about that here. After all, it's 6.3 volts, or maybe it's 6 volts with loading, or maybe it's even a little lower. But we're only after 1.5 volts to make the ohm meter circuit work. So we don't care if this sags as far as this circuit is concerned. What we do have to do is rectify the 6.3 volt AC filament circuit, so we need a diode. There are some battery eliminators which use a full wave bridge here, and for various reasons that's a bad idea, at least with this design of VTVM. It can cause things happening you don't want to have happen. It's also important to get the polarity correct relative to circuit ground. I mentioned before that one side of the filament circuit is grounded. That needs to be the same electrical point as the minus side of the battery eliminator. So we have to make sure we put the diode on the side of the filament circuit which is not the grounded side. And you're not going to be able to easily tell that with just slapping an ohm meter on it, because you've got the very low resistance of the filament winding on the transformer. You've got the low resistances of the two, actually 3 filaments of the 2 vacuum tubes, and the low resistance of the pilot lamp all in parallel. It's going to read almost like 0 ohms. And therefore, just slapping an ohm meter across here on one of these to ground, they're going to give you the same reading essentially. You really have to study the wiring, and if there's a circuit board, you need to study the connections on the circuit board to know which side of the filament circuit is connected to the circuit ground. And make sure that your diode connects to the other side of it. Because the voltage here is not going to be any higher than 6.3 volts, you can use a pretty low voltage diode. Really, a 1N4001, which is very common, a general purpose silicon diode with a low voltage rating. It's still going to be way higher than the voltages we're dealing with. But you could use any diode in that series or equivalent series. Again, you're probably not going to find a diode rated less than 50 volts, and most of them will be at least 100 volts, and you're only dealing 6.3, so pretty much any diode will work here. Just a normal semiconductor diode. Then you need some sort of filtering. You don't have to worry about it too much because the voltage is so much higher and the input of the rectifier or the regulator than the output will be. So even with a lot of ripple on it, and it's a low frequency ripple, you don't even really have to filter this and this will work. But for best results, you should put some sort of filtering here because the current is fairly low. You'll see some people using a 470 microfarad cap. The commercial battery eliminator that I used in the example in this video has a 1000 microfarad cap. Keeping in mind when you're in the 1 point or the R times 1 range and you're pulling quite a lot of current out of here, the ripple is going to be a lot higher, and therefore more filtering here will be advantageous. You'll also see a lot of people throwing a small value capacitor in here, and indeed the commercial battery eliminator I used in this example has a 0.01 microfarad capacitor across it. That doesn't do you any good here, but it doesn't hurt to have it. But if you're building your own from scratch, you don't need to put that in there. You do need this. Then you're looking at the LM317. It has the input, output, and adjust terminals. And it needs a small heatsink, but not a very big one. Just a chunk of aluminum or a piece of aluminum sheet metal screwed onto the heatsink tab of the LM317 would probably be more than adequate. And here is a diagram of the LM317. Looking at it from the front, you've got the heatsink tab up here, you've got the plastic body, and you have the 3 leads. The left one is adjust, the middle one is output, the right one is input. This is very different from your normal 3-terminal voltage regulator pinout, which is usually input, ground, and output. So you can get into a lot of trouble using an LM317 if you don't check the pinouts against the data sheet or a reference like this. Okay, how do we get this LM317 to output 1.5 volts instead of some other voltage? Well, it's done with these two resistors here. And this is where another mistake is often made. People just start messing around with resistance decade boxes and things like that until they get the right voltage. And that can be done, but it's not optimal. There's a reference generator inside of here which is expecting a certain voltage from here to here. And if you have a really wrong value resistor out here, you may be pulling more current through that than there should be, and you may get less than optimum results. National Semiconductor, who originated the LM317 design, always recommended that you have a 240 ohm resistor in this position and then vary this resistance as needed to get the desired output voltage. 240 is an odd value, 220 is much more common, so when I do these I always use 220 ohms. And then if you do the math, you'll find out that a 47 ohm resistor here will give you just slightly more than 1.5 volts on the output. And then we do need to stabilize it. They do recommend that a small value of electrolytic capacitor or a tantalum capacitor be used on the output just to help the IC stability wise. So I always use a 1 microfarad 50 volt capacitor. In small capacitance electrolytics, you usually don't find resistance or voltages less than 50 volts anyway. The parts are really small to start with. You don't really benefit from having a lower voltage. The pure math on this says I would get 1.52 volts approximately with these resistor values. And then you just take the output voltage here and connect it to the same point in the VTM circuit where the plus side of the battery normally connects to. And the easiest way to get to that is by look at the rear deck of the range switch, the terminal that's referred to as 1. Of course, it doesn't say 1 on the range switch. You'd have to have one of the Heathkit assembly manual diagrams to show you which one is terminal 1. So I say here, look for the 9.1 ohm resistor on the rear deck of the range switch and see where the wire from the battery plus connects, and that's the place where you want to connect this battery eliminator. Of course, you never use the battery eliminator if you actually have a battery in the battery holder, because then this will try to charge the battery. The battery's not designed to be charged probably, and this isn't designed to be a battery charger. So this is only to be installed if you no longer plan to put the battery in the battery holder. However, if you decide you don't like this and want to reinstate the battery, all you have to do is disconnect this one wire. Then you can put the battery back in and everything's great. So I have some more notes here. It talks about the diode, that it only needs to be a 1000 or 4001, and that the two resistors, quarter watt resistors, are fine. While you could probably get away with 5% tolerance, you should really use a 1% tolerance part. They're pretty readily available these days, and you'll get a lot closer to the desired voltage. And it says if you use the 47 ohm resistor as shown in the schematic up here, you should get a value of slightly more than 1.5 volts. I actually have a typo here I have to fix. That should be 1.5 volts, not 5 volts. And if you find that the voltage is too low for some reason, probably due to resistor tolerances, you can adjust that by adding another small resistor in series with the 47 ohm, making it a little bigger. Or you could replace it with just a bigger value resistor. Another standard value is 51 ohms. You could put there instead of the 47 ohms. Or you could do like the commercial battery eliminator did and have a 100 ohm potentiometer here. Or actually the commercial one has, I think, like a 10K potentiometer. But if you're building one from scratch, you only need a 100 ohm potentiometer, and then set it to about its mid point of rotation, which will be around 50 volts or 50 ohms, and then dial it in from there to get exactly the voltage you want. A problem with the commercial battery eliminator, like I'd said earlier, is it's based on a generic block that is intended to be a power supply going up to 40 volts. So they have a 10K resistor here, so it can be adjusted, or it's a 10K potentiometer, and they have that so you can have a wide range of resistances here, and that can allow you to adjust from the lowest that the LM317 can put out up to about 40 volts. Well, even with a 10-turn potentiometer, when you're trying to adjust down to about 1.5 volts out of a 40 volt possible range, you're getting into a kind of a touchy adjustment where just barely breathing on the adjustment screw can have you go pretty far away from where you want to be. So I don't even recommend using the pot. I recommend sticking a fixed value resistor, do the math, figure out what the value should be, stick it in there, and as the voltage here is not critical, you want it to be stable, but it doesn't matter if it's 1.52 or 1.5 or 4.95 or whatever, as long as it's stable. You can adjust the rest out with the zero or with the ohms adjust control on the front of the VTVM, and because this is regulated, it's not going to go anywhere from that point on. So here's the math. The formula for V out is 1.25 times what you get when you divide 47 ohms by 220 ohms, or whatever resistor values you put in there. Divide that by that, then add 1 to it, take the result and multiply it by 1.25. That's a constant. That's actually the internal reference voltage of the LM317, by the way. And that'll give you your output voltage. And you can use basic algebra to flip that around and calculate what the resistances should be based upon the desired voltage. But that's the formula there, and it does work out. I've built them, and you get really close to the voltage you want. And again, I'll say it one more time. The actual voltage is not critical here, and of course it wouldn't be because the meter is designed to have a battery there, which isn't a precise voltage source anyway, and with use it's likely to deplete down to something less than 1.5 volts, and you can just dial that out with the ohms adjust on the front panel. And of course it'll get worse, and Heathkit even mentions this in the manual, because it draws so much current when you're in the low resistance ranges. You want to take your measurement and disconnect, because number one, you're depleting the battery quickly with so much current coming out of it, and secondly, the voltage from the battery may be dropping as you're taking the measurement, and therefore your reading is going to be skewing, and you're going to say, what's going on here? You know, I have to keep readjusting and remeasuring, and the values shifting, and that's one of the main advantages of using the battery eliminator, especially one that is really regulated here, because it will hold that output voltage where it needs to be even when there's a substantial load on it. And even if the filament winding sags due to the load, it'll still be compensated for by the voltage regulator, the LM317. So this is really the way to go. One other thing about these battery eliminators using the LM317, the 317 is not good at protecting itself against reverse voltages. In other words, when you have a higher voltage at the output than you do at the input. So a common recommendation is to put a diode from the output facing backwards to the input. So the cathode is facing the input. Then if you get a higher voltage applied, it won't come from the LM317, it'll be from something that's connected to the output over here. If that happens to have a higher voltage than whatever the input voltage is, it'll just bypass the LM317 instead of damaging it. And if you tie a capacitor across this lower resistor to ground, like across the 47 ohm resistor, sometimes people do that if they feel they need extra stability. It's not required in a circuit like this, but some people put it on anyway. And then depending on the capacitor and some other factors, you might envision a situation where that capacitor could discharge and also cause damage to the 317. So they'll put a diode around that in some way, shape, or form. There's different ways to do it. In a circuit like this, that diode I don't think would help at all. It just makes it more complicated. As for the diode going from output to input, in normal operation you're not going to have anything out here that's going to produce a higher voltage than the filament voltage. And because the capacitor here isn't that big and some other factors, it's big enough, and there should be almost no capacitance out here except for this guy, 470 over 1 or 1000 over 1. This guy is going to maintain the voltage here while this one is long since depleted, and you shouldn't have a situation where this would cause a higher voltage and therefore a reverse current flow. You probably don't need that diode, and I haven't put it on any of the ones I've done. The only situation I can think of where that would possibly be an issue is if you connect the test leads to something besides a resistor, or if you connect it to a resistor in a circuit that's powered, you could potentially get some backflow from that would be a high enough voltage to result in a higher voltage here than there is here, and it could possibly cause some damage. So if you are putting one of these into a meter that you think might be used that way and you want to protect against it, it certainly won't hurt to put a diode going like that. But I don't show it here because I think it's probably not going to benefit enough to make it worth putting it in. And just for yucks, I'm including the quick look at my third page of the document I created. It has a circuit block by circuit block description of what's going on. It has diagrams of the two switches, the range switch and the function switch, confirming what the rest of the diagram is calling the various decks and sides of the decks where they have two sides, and all of that reference to which side the shaft comes out of, and front to rear relative to the meter face. So that just clears that up. The abbreviations shown here are the same ones used on the schematic and elsewhere on this 3-sheet diagram. Then this is like a little abbreviated user's manual for the operation of the VTVM. It goes through basic practices and talking about making sure you warm it up first, how to use the zero adjust, how to do DC voltage measurements, AC voltage measurements, resistance measurements. It talks about the fact that the meter face is scaled to also read decibels. It talks about what decibels are, just in a nutshell. It talks about you can use the direct reading scale, or depending on which position the range switch is set in, you can have offsets to get the correct decibel reading. It talks about the accuracy of the meter in the different functions, DC volts, AC volts, and ohms, and how in particular the meter is very susceptible to stray electromagnetic fields when you're in the 1.5 volt for AC measurements. Talks about that. Talks about the tolerances. It talks about electrostatic charge on the face of the meter, which just from wiping it with a cloth to get some dirt off of it, you can put a static charge on the face of the meter, which will skew the meter winding. It reacts with the pointer, and how to remove that by 2 or 3 techniques. And it also talks about that the meter doesn't really have any protection devices in it. A lot of multimeters will have back-to-back diodes across the meter movement. These VTVMs do not. It'll talk about there may be active components, fuses, what have you. None of that exists in here. However, the balanced bridge circuit, just because of the way it's set up and the limitations of what it's able to do, when you do overrange it, it tends not to damage the meter. There's a certain dampening and limiting effect from the balanced bridge circuit that offers some small measure of protection to the meter movement. Although if you just slam it hard on a severe overrange, you might bend the pointer, the needle of the meter, which would require all sorts of dismantling and trying to straighten out and possibly breaking it. So, as it says elsewhere on here, when you're measuring anything where you're unsure of what the value is, it's good to start with the highest range, whether it's voltages or ohms, and then back down until you start getting a reading. And then always adjust for the reading that has the meter most centered, because that's where the greatest accuracy is achieved. And then finally, I have a note here on replacing the vacuum tubes. I already mentioned it earlier in the video, but it talks about the 12AU7 and some potential substitutes and so on. Oh, it also cautions about not trying to just replace the 6AL5 twin rectifier tube with a couple of regular silicon diodes. It'll work, but you'll have reduced accuracy. It is possible to make it work properly with diodes, but you need to fudge it a little bit and also make an alteration in the circuit by changing some resistance values from the factory values in order to get it to work right. And indeed, Heathkit did offer towards the end of their production of VTVM circuits or kits, they offered solid-state replacements for both the 12AU7 and the 6AL5. The 12AU7 one had 4 FETs in it, and the 6AL5 had a couple so-called special diodes. I don't know what kind they were, but something with the specifications that minimized their problems, and even then you had to change one resistor value and remove another resistor to get it to work correctly. So I'm just saying here I don't recommend doing that. The 6AL5s are still readily available in new old stock and pulled out of circuits and tested, and they last practically forever. So it's not too hard to get your hands on one and just use that.